All right. Good afternoon, everybody. Hopefully, we're having a good day. Just a reminder, the homework is due tomorrow for assignment. I believe it's assignment 2, the recurrence relations one. So hopefully, we're doing well on that. I'll be in office hours tomorrow, in person and through WebEx as well. So that way, if you have any last minute questions, anything, of course, you can still ask. So I guess for today, let's go ahead and let's continue from last time's material, which was that divide and conquer approach to matrix multiplication. So let's start the screen share here. Let's begin. Okay, so last time what we did was, let me just recap this a little bit. We had this original matrix given to us. So we want to have A times B, and we want to sort of compute this result into the matrix C. So what we did was the concept of doing this divide and conquer approach was you broke this matrix A and B into 4 quadrants and then multiplied quadrants out. So we first wanted to compute, let's say, the top left quadrant of C, which is C11, and it has the following formula: A11 times B11 plus A12 times B21. So we take A11, this whole submatrix, multiply it to B11, then take A12, multiply it to B21. And of course, we do the same thing for the rest, but we'll just do that one part so far. So A11 and B11 are going to be smaller submatrices. So when we do this, we have to recursively compute each one of these as well. So when we went to do A11 times B11 first, we had this matrix. This whole matrix right there, this submatrix, was A11 of that original A matrix. And then this is going to be the B11 for the original B matrix. So you have to recursively do this as well. So in this situation, if you divide this into 4 quadrants, we have these size 1 matrices in this situation. So we have to recursively do the same thing. You have to first compute A11 times B11 plus A12 times B21. But in those cases, though, when we pass in A11, this A11, into the recursive function, it's going to hit that base case because we have these size 1 by 1 matrices. So each one of these will take constant time to compute, and we add these up. So then we end up getting this matrix. So we just take 6 times 12 plus 12 times 2, and 6 times 11 plus 12 times 4 goes over here. So we just sort of do it in this type of fashion. And these would all take constant time because each of these submatrices have a size 1 by 1. So then we have this result. This result gets returned back to the previous function call. So we actually originally did this. So we had to compute these recursively. We got them recursively, and we're going to add these up. So we actually first have to do this A11 times B11 first, which gives us this matrix. Then we have to do A12 times B21 to give us this matrix. And again, we're passing in A12. This is going to be the A12 matrix, and we can break this into its own A11s, A12s, and so forth. We multiply these two out to get this result. We add these up to get this matrix. This will be your C11 at the very end. So all we had to do is just basically first compute this submatrix recursively, then this one recursively, add these up, and then C11 gets assigned this submatrix. Now, same idea, we want to go ahead and now compute C12. So C12 is computed using this formula. So we have A11 times B12, which are 2 submatrices for A and B. We recursively compute these. So A11 is this submatrix, B12 is that submatrix. And we compute them recursively. In this case, we again divide these submatrices into 4 quadrants, but then in this case, they're going to be size 1 matrices again. So each one of these, we have to compute A11 times B11 plus A12 times B21. Same idea, we do the same formula on the smaller set matrices, but luckily it will take constant time for each one of these. So we can, in constant time, compute all of this entire matrix to get this matrix right there. That's going to be A11 times B12. Now we have to compute A12 times B22, which is going to be this. We have these two matrices. We break it down into 4 quadrants, and we compute this result. Then we take this red matrix plus this one, to get this matrix. Return that back up to the original function call, which will store that into this matrix right there. So that's where we kind of left off last time. Let's go ahead and finish up the rest of the matrix. So we have to now do, I believe, I think C22 next. We have C12, then we did C11, C12. We have to do C21 next, I believe. Yes, C21. Okay, so we first have to get A12 times B11. Well, in this case, A21 is going to be the following matrix. You first have to do this first multiplication. So A21 is going to be 9, 4, 12, and 13. And then B11, well, that's going to be just simply 12, 11, 2, and 4. So this is going to be essentially your A21 matrix, and this one's going to be your B11 matrix. So again, we can break this down into 4 quadrants. And we can get, this is going to be the A11 for this smaller matrix. A21, sorry, A12, A21, A22, B11, B12, B21, and B22. So we have to do those 4 formulas to compute this result. But luckily, each one will not do any more recursion because so A11 in this case is single value, so is B11. So each of these will take constant time to compute. So the result of this is going to be the following matrix. Let me just go ahead and put some more room here. It's going to essentially just be 116, 115, 170, and then 184. So I kind of shortcutted this a little bit because I don't want to have to manually do all that work. It would take too long. So we can kind of shortcut this part, but it's going to be our first. So this is going to be the result of multiplying A21 by A11. We get this result. So now we have to compute A22 times B21. Well, for original matrix, the following. So A22 is going to be this matrix. It's going to be 5, 1, 14, and 15. And then the B21 matrix is going to be the following: 1, 3, 8, and 4. So again, we have to do this recursively once again. So we have to break this down into 4 quadrants. And this is going to be the A11 of this smaller matrix, which breaks it down even further into these single element matrices. So then we have to apply that same sort of formula for the C11, C12, C21, and C22 on this instance, which is very simple to do. They're all going to be constant amount of work because they're all size 1 matrices. So the result of this, sorry, we kind of worked this out previously. The result of this is going to be 13, 19, 134, and 102. That's going to be the result. So now we have these 2 red matrices. These are the 2 results, essentially, of, well, it's going to be the result of, so you have A12, B11, A22, B21. So we have these 2 matrices as a result. We add these up to get our final product, which will essentially will be the following. We're going to have 129, 134, 304, and 286. So the matrix here in green, that's going to be the final result. So we go ahead and return that back up to the very topmost function. This is going to be essentially your C21 matrix, which gets returned right there. And we're going to assign that into this quadrant right here. So we're going to assign that right here, which is going to be, well, let's copy it back there. So 129, 134, 304, and 286. So if you compute this whole matrix the normal way, this so far is the correct result. We don't have the last quadrant done, but this is correct. So I did verify with a multiplication of two matrices a normal way, and I got the same results. So that made me feel confident that I wasn't messing up this example. So now we have to do the last one, which will be C22, and then we'll be officially done with this problem. Let's go ahead and do the last one just to finish this off. So you have to do C22 next, which will simply just be A21 multiplied by B12 plus A22 multiplied by B22. Okay, so what's A21? Well, we just take that from our original A matrix, we just take that quadrant, A21, which will be just 9, 4, 12, and 13. And then B12 is going to be this matrix, 5, 6, 8, and 10. So we have to multiply this out. We first have to, again, do a divide and conquer on this instance. But once again, we're lucky because they'll be single-sized matrices, 1 by 1. So each of these function calls would be a base case, so it would not have to recursively do any more work. So then what's going to happen is we're going to go ahead and work this out. So we're going to multiply all these. So I'm going to go ahead and just put the result of this matrix over here, which is going to be 77, 94, 164, and 202 using the formula that we've already done before, but this one it'll be all constant amount of work. So just using that formula, you apply that same formula on this small instance, and you should get this result. So this is going to be the result of A21 times B12. Now we have to do A22 times B22. So we just go to our original matrix A and B and get those required quadrants out. So A22 is going to be this matrix. So it's going to be 5, 1, 14, and 15. Another one, B22, is going to be this matrix. It'll be 7, 9, 2, and 1. So again, we divide this up into 4 quadrants. 2, and I guess, did I put it over here on this one? Okay, fine, I'll just write this over here as well, and just to be consistent. But we create these quadrants out of these smaller matrices and do exactly the same formula on this small instance of the problem. And then same idea here. We break this down into their own little quadrants. We have B11, B12, B21, and B22. So we have to use the same formula to compute this matrix, which is going to give us the result of this. We have 37, 46, 128, and 141. So it's going to be the other matrix we computed recursively. So we have this one and this one. We have to simply add these up, which we'll just do right over here. And we're going to get the result of this matrix. We're going to get 114, 140, 292, and 343. So that's going to be the C22 matrix. We return that back up to the original function, and we assign this into that bottom right quadrant. So it returns that result back up, and C22 is assigned to that result, which we're going to go ahead and write that right over here. It's a long problem. There we go. So this will just be simply 114, 140, 292, and 343. So I verify this, and this is the correct product, but we did this in divide and conquer fashion. All we had to do is break this into 4 quadrants, and then do the same exact work on those smaller size matrices. And we have to keep recursively breaking this down until finally we pass any size 1 matrices into a recursive function, which hits the base case, and it can finally start computing and then returning results back up and adding them and so forth. So that's basically how this works. So it's very repetitive, but it's not a very complicated problem. It's just repetitive. It's just a lot of the same things. As you can see here, this gets kind of boring to do all this, but that's really what we have to do. There's not much else. It's not really a very hard problem to work on. So, okay. So basically, let's go over now the time complexity analysis. I will definitely post these notes up online for sure. So let's go ahead and just go over time complexity analysis for this problem. So basically, what's happening here is we want to create this sort of recurrence relation. So once again, what's going to happen is we're going to sort of break the matrices into n over 2 by n over 2 submatrices. So we are constantly dividing this problem in half every single time. We're dividing it in half to the row and column amount, but we're going to do, kind of log base 2n number of levels of recursion. So we are definitely dividing in half is the idea here. And then we have to perform sort of 8 multiplications recursively. So when you multiply 2 matrices together, that's going to cause us to pass in the smaller n over 2 by n over 2 size matrices into each recursive function. And it's going to recurse further and further until we have a base case of size 1. So we do 8 multiplications of these n over 2 by n over 2 size matrices. Then we're going to have to add the results after multiplication, which multiplication here is going to be a recursive process to solve each Cij submatrix. And we're going to basically add up. So we're going to add several n squared over 4 matrices. So this adding part is going to be where we sort of combine the results using this divide and conquer approach. So this addition takes theta of n squared, because we're adding up these n squared over 4 matrices together, which the runtime will be theta of n squared. So the recurrence, well, now we kind of see the components here. We break it in half, 8 multiplications, and then we combine them using theta n squared times. So we have the ingredients right there. Now we can go ahead and have our recurrence relation, which will be the following. And of course, as always, T of 1 will be 1. So size 1 matrix takes constant time to multiply. So, it's nice being able to express an algorithm in terms of recurrence relations because we have so many ways. We have an arsenal of ways to solve these recurrences. This one we can very easily apply master theorem to do, is we don't have to even expand it. So the expansion method we did in that first week or two was just to sort of get an idea of how these actually work. Now, maybe for like homework and for exams, if I tell you you have to do it, expanding it out, then you have no choice. But once you kind of understand this, then, we can just use master theorem to solve this. So I believe this will involve case 1 of the master theorem. So this one is going to be theta of n cubed. So T of n is an equal, essentially, theta of n cubed, which Okay, so once again, just like what we had for the multiplication of two numbers, we applied divide and conquer again, and did all that fancy divide and conquer recursion just to do the exact same runtime as if we could have done it using the regular, elementary school way, or I guess matrices would be the maybe high school way. You multiply two matrices. So that method that we did, that the high school approach, was theta of n squared. So is this. So okay, great. So what? I mean, that's not a big deal. We didn't improve anything. But once again, though, just like for the multiplication of two large numbers, we have the divide and conquer approach. So we can easily split this up into pieces and make this work. So once again, what if we can find a way to do maybe one less multiplication and we can get a better runtime than theta of n cubed? That's a great idea. So let's go ahead and try that approach. Now, for the number multiplication had a very elegant solution. This one does not. This was a very ugly solution. So let's go ahead and just try to list this out. So we're going to use this method called Strassen's um, matrix multiplication alg, which is short for algorithm. Okay, so luckily, memorization for this class is never the best idea because this one, memorizing this is going to be really not very easy. But I'll list it out though because for homework, I'll have you guys work out Straussen's algorithm just as an exercise. So it's very much based on this divide and conquer, but we do a few extra additions to avoid having that one. So we try to reduce our problem by having one less multiplication, but by doing that, we have to do a lot of additions to do this. So I'm not going to use a big matrix for the homework, maybe a 4 by 4 matrix, because I think that will be kind of, good enough. But anyway, let's begin. So this is the formula from the book. So we're going to do the following. So I'll list it out here so you can avoid having to have to read the book. So basically, these A12s, B12s, and all that is just sort of these quadrants of our original matrix A and B. Nothing really too different there. So I don't know how this was actually created, but I'm just going to go ahead and just, actually you can prove this actually does work, but I won't prove all that right here because it's going to take long enough. But we're going to do, oops, let's see, S4 is minus B11. Yeah, this is really pretty crazy. So we have A11 plus A22, and then S6 will be B11 plus B12. S7 will be A12 minus A22, and then S8 will be B21 plus B22. We have only two more of these, and then we have several more. So S9 will be A11 minus A21, and then S10 is going to be B11 plus B12. I'm going to make sure my notes are correct, but I will zoom out so we can see all of this. Okay, and verify I'm correct. Here's a 1, 2 minus B22, A11, B12. It looks like so far so good. Yes, okay. Looks like it's about right. Okay, so we first have to compute these 10 submatrices. Now, once again, each of these submatrices, a B11, B22, A1, all of these are going to be n over 2 by n over 2 in size, just as always. So each sort of A, I, J, yeah, so of course, I zoomed out right here, but I'll definitely show the entire thing like this so you can see the entire formula. Absolutely. So basically, all these additions together. So to compute all these S1s, so to compute sort of to compute S1, oops, S1 to S10, it will take 10 n squared over 4 time. So overall, this takes theta n squared to do all of these. So to compute S1 to S10, all that additions will take theta n squared. Now the problem is we have to do 10 of these. So 10 is a big-ish number, but not, big enough compared to what n could possibly be. So we have to do all these additions, which take theta n squared times. So, adding these submatrices is, you can't really improve on that too much. So that's going to be the first initial step, is we compute these S1 to S10s. Okay, so we can literally just follow the formula. We can very easily get these A and B submatrices. We can extract those out, no problem, and add those up. So this part is not really too hard, just very tedious, but not hard. So now we have these S1 to S10s. I'll work out the rest of these. So now we're going to create these other matrices now. Only if it won't be as much. So A11 times S1. P2 is going to be S2 times B22. P3 is S3 multiplied by B11. P4 is, the heck was that? P4 is A22 multiplied by S4. And then P5 will be S5 multiplied by S6. P6 equals S7 multiplied by S8. And then the last one, P7, will be S9 multiplied by S10. Let me verify I'm correct. So A11, S1, S2, B22, S3, B11, A22, S4, S5 times S6, S7, S8, S9, S10. Okay, there we go. So, I mean, once again, all these A11s, B11s, all these submatrices of A and B will all be n over 2 in size. And also, all the S1s to S10s are also going to be n over 2 in size. So really, we're doing the same kind of divide and conquer approach, because we're passing in two matrices and we're multiplying these, so these will all be done recursively, just like before. But notice here, we only have to do 7 multiplications, not 8 in this situation. So each of these matrices you're going to be using are all going to be n over 4 in size. So each multiplication is done recursively. Using two matrices of size n over 2 by n over 2. So the same problem, really the same as we did before. But now we only did 7 multiplications over here. So I'll put a bullet here. I want to do 7 multiplications, not 8 this time. So that's going to give us an improvement. And now we have all these P1s through P7s. Now we have to go ahead and compute the C11, C12, C21s, and C22s. So I'll just kind of leave this here just for a second before I write down the last few parts. But hopefully we have this written down or screenshotted or whatever. But I will post these notes up onto Canvas either way. So also try to make sure the cutoffs aren't going to be messed up on the. I know there's some cutoffs sometimes, which doesn't make a big deal, but for this one, it could make the problem. It might make it hard to read if the cutoffs are in awkward spots. So I'll make sure the page cutoffs are in good spots as well, so it's easy to read this. But I will definitely post this up on Canvas for sure. It's also in the book as well, but this way you don't have to read the book. So anyway, now we have those parts done. Now we have to simply compute C11s through C12, or from C1 to C22. So we're going to have the following results. So P5 plus P4 minus P2 plus P6. That will give us C11. Then C12 is going to be P1 plus P2. C21 equals P3 plus P4. And C22 will be P5 plus P1 minus P3 minus P7. So you can actually show, using algebra, if you sort of apply these formulas, that if we add P5 plus P4 minus P2 plus P6, it's going to, so because these subtractions kind of cancel out certain matrices, it will actually give us the original C11 value. So if, let me just go back to my notes just for a second so I don't mess this up. So for example, C11 originally was A11 times B11 plus A12 times B21. Well, that work right here, these addition subtractions, is going to give us that result. Now, I'm not going to show that right here, it'll take too long, but it will give us the original C11 as it was supposed to be. So each of these subtractions and additions, again, this will all take theta of n squared again, because each of these matrices, these P1s, so P1 through P10s, are all going to be n over 2 by n over 2 in size, so they're going to be quadratic in size. We do a bunch of additions and subtractions. We're going to do several theta n squares. So the deal here is that we do only 7 multiplications, but we do a lot of additions. I mean, we do a lot more than we did before. I mean, look, we can count how many there are. There's a lot, like I think around 20 or so additions and subtractions. So it's a lot. That's a pretty big constant value. But by doing that, though, we only have to do 7 multiplications. So 7 recursive functions happen. So all of this will take theta n squared, and to compute our original P1s through P10s also takes theta of n squared. So again, that conquer part, or that constructing the part, takes, again, theta of n squared total. Now it's going to be a big constant, it's like 20 theta of n squared it will be actually, but that's still going to be theta of n squared. If n is big enough, that constant shouldn't make a difference. So this combining part still takes theta of n squared, but we do only 7 multiplications. So for the Strassen's algorithm, it's going to actually follow this recurrence. And of course, once again, size 1 matrix takes constant time to compute. So again, if we use the master theorem on this, we get case 1 again, I believe, but this will actually give us T of n equals theta of n up to the log 2 of 7, which is roughly going to be theta of n up to, let me see if I have this written down here. Oh, wrong spot in my notes. So 2.807. So 2.807, roughly around there, which is actually going to be better than n cubed. Not a lot better, but it's asymptotically better after all. So this approach is a better idea. But with Strassen's algorithm, though, the problem is you have to do too much extra busy work, which could cause a round-off error in certain moments. Also, if n is pretty small, then it's actually a big-time overkill, which you'll see when you have to do the assignment using Strassen's algorithm. So I first worked out that plain divide and conquer approach, and this one really does build off of it. Just you have to do a lot of extra work, which I guess will, I mean, it'll be more busy work for the homework, but it's not a hard assignment if I have to have you do this. It's just busy work. It's just annoying, but not really hard. So, I mean, there are classes before 477 where the assignment is hard and it's a lot of work. This one at least is just a lot of work, but not too difficult. So basically, once again, when do we use Strassen's algorithm? Well, I guess I could sort of say, well, why wouldn't you use it? Because it could be better than a regular matrix multiplication approach. But obviously, n has to be pretty large because we do a lot of additions. So that's going to be the problem. Now, of course, for a homework assignment, we're going to have n just be, we're going to have just sort of these 4x4 matrices instead to make this problem a lot simpler. So you have to do one level of recursion, and then we have these 2x2 matrices. You can kind of just cheat and compute that submatrix by just saying, well, they're all base cases, so you can just kind of do it how I did it in class here, just to make it simpler on you. So it won't take that long. We'll make it a little bit less time, but in theory, you'd want to have n be pretty large to really even try to use this approach. But if n's big enough, you can get a better runtime than using the traditional algebra 2 or high school method or that plain ordinary divide and conquer method. So those are two kind of sort of our two new, I mean, I guess I'm not sure if this was covered in CS302. I don't cover this in CS302 at least, but this was like these two divide and conquer approaches. So of course, for our next homework, you have to sort of work these out. So any questions on this before I sort of go on to a new topic? But I will, of course, post all of these notes onto Canvas after class today. So I guess I'll just go on to a new page here. So let's go over a known algorithm, Quicksort. I'm guessing you probably had to have learned Quicksort when you were taking CS302. And once again, it's another divide and conquer approach. Because Quicksort, well, how does the divide and conquer really work? Well, let me just go ahead and let me just illustrate this out if in case you forgot. So again, I'll just put this here. It's also a divide and conquer algorithm. As you might already have known, you've already learned this, I would imagine, before, but let's go ahead and recap it. If in case it's been a while since you've done this algorithm, why not let's recap this once again. So basically the idea is to do quick, so we first have to choose a pivot, which is really any element in the list. Any element can be your pivot. So now what we do is we have to partition the list into two pieces. So we have to sort of run the partition phase, which is going to separate the list into two pieces. One of them, so a piece, so I guess sort of a sublist, if you will, a sublist with elements less than the pivot, and another sublist, so a sublist with elements larger than the pivot. Now, for duplicates, you could do the following. You could have one sublist be less than or equal, and other one be larger, or have one sublist be less than strictly, other one is larger than or equal. It's up to you how you want to do that. We're just gonna not worry about sort of duplicates for right now, but that's how you would actually, have to work this out basically. So, but the idea is you run this partition phase to separate in two pieces, and this partition, well, it has a certain runtime. So partition takes theta n time. Because really we have to go through this list and we have to do comparisons and we break it in the middle somewhere, or hopefully somewhere, not at the, we want to break it somewhere in the middle of the list, somewhere in the middle, whether it could be at the very beginning or very end, that would be very terrible, but practically it might be somewhere in the middle-ish is the idea, and it takes theta of n time to do this partition. So I guess I can also explain why it's theta of n once we actually do partition. But for right now, though, I'll just give the answers theta of n. And if I have time, I can also discuss why that's the case. But I'm guessing in 302 you might have already covered that, but I can talk about that a little bit if I have some time. So basically, let's see how does partition actually work? So actually, I already sort of did it like this. I already explained partition in a sense. So the idea is once we partition in two pieces, we have to run Quicksort on each piece. And then we've successfully sorted the array. So we have to first break it apart in two pieces, which partition will do in theta of n time. And then we recursively sort the two halves separately. That's going to be your sort of divide part. And the conquer part is we first have to break it apart with partition, and then we have to recursively call on the two sublists. So the idea is, so the more details of how partition works. So I guess I'll have some details of partition. So you're given basically, so you're going to be given an array and also given the endpoints, which I'll call L and R. So R being the rightmost endpoint, L being the leftmost endpoint. So typically you pass the same array every single time into the function, and you pass in which parts of the array are you going to currently partition at this moment, because you're going to cause partition many times on different size arrays when you do quicksort. So what I always do is I'm going to first choose a pivot and then swap that pivot into index, or swap it with index L is a better approach. Swap, so pivot with the element at index L. So the way I was kind of taught quicksort and how I like to think about it is I have the pivot sort of out of the way. So I put it to the very far left position, and then I'm going to process all the elements to the left of L. So we're going to have these two counters. So set counters I, which will be set to L plus 1, and J, which will be set to R. So I and the J's are going to kind of move through the list. So I increments by 1 every time the element at index I is less than a pivot. I'll write this over here. So we're going to increment I by 1 when the element, so A of I, is going to be less than the pivot. And we're going to decrement J by 1 when A index J is larger than the pivot. Now, of course, we could have it where it could be less than equal and have this one be strictly larger, or we can do it like this. Doesn't really matter, but I'll just assume we'll have no duplicate values in our lists. Now, of course, what if we have a case where A of I is bigger than a pivot and A of J is less than a pivot? So if that happens, so I'll just put this here. So if A of I is larger than a pivot and A of J is less than a pivot, if this happens, well, we can simply just swap A of I with AJ, and then just have J I plus plus and J minus minus. So we can just swap them and then we can move it. Once we swap them, obviously index A of I, that value will be less than the pivot, obviously, at that point. So we can definitely move I. And also j element has to be larger at this point, obviously, so we can move j as well, and we keep this going. And then once j is going to be less than I. Yeah, so once that happens, then we partitioned the list so we can swap the pivot value, which will be, swap A of L, which that's going to be our pivot. Our pivot will reside in index L. We swap that with the element at A, J. So now the pivot will be in its correct final position. So that's sort of how partition actually works. So, yeah, so I guess what I could do now is after I explain this, let's do an example of quicksort, since I could even possibly, on an exam or homework, have you trace out quicksort, since that's the most interesting sorting algorithm out of all the sorts you do in 302, because bubble sort is kind of boring. I mean, bubble sort has a cute name, bubble sort, but it's really has not much there. And search and sorts is the interesting one. I could do a little shout out at the end with some of these other sorts, but the most interesting one, obviously, was quicksort. So we're going to do a lot of analysis and do other work, and because quicksort has a very interesting sort of behavior, that's why I chose quicksort to be the one we're going to focus on for the most part in this class. So let's do an example of quicksort and just get an idea, sort of recap quicksort from 302. So I'll have an example right there. I already have an example already chosen, which will give us a nice broad example of this algorithm. So we're going to have 5, 1, 3, 10, 4, 2, 7, 9, 18, and 12. All right. So to run this algorithm, we're going to first have to pick our pivot. So right now, L is going to be basically right here. This will be our L, and this will be our R, like this. And I'm going to choose my pivot, so anything can be my pivot. I'm going to pick 5 as my pivot just because. I'll just maybe just have P here for pivot. And then I'm going to have my I and J counters set up. So I will be over here. I guess J will be set to R originally. So pivot is 5. So I just picked 5 just because. Anything can be the pivot. If I would have chosen something in the middle, let's say 4, I would swap the 4 into 5 and have 4 be in the very left, so it's kind of out of the way. So we're going to mostly process from I to J, and L is kind of sitting there by itself. So to run quicksort, you first check. So element index I is smaller than the pivot, so we can move I by 1 over to the right. And element at J is larger than the pivot, so we can move J. So that's the first iteration of partition. Then of course, we again check. So I, the element at index I is less than the pivot, so we can move I comfortably. And then J, the element is bigger than a pivot, so we can move J comfortably. And then we have the case where, okay, I contains a value bigger than a pivot, so I can't move. But J, however, can move, because the element index J is in fact larger than pivot, so J will move. So we only swap those values only if both I and J can't move. But since J can still move, we are progressing through this partition. Then of course, we check once again, I is a larger value than the pivot, so we can't move I. And J can again move because J is actually contains 7, which is bigger than the pivot, so J can definitely move, like that. And now we have the situation where, well, it looks like j can't move and I can't move because I has a bigger value than the pivot and j is a smaller value than the pivot. So we have to swap these two values. So we just have to perform a swap over here. Because we can't really progress in this situation. So I guess I'll rewrite this list over here at the bottom. So we have 5, 1, 3. I'll put a 2 over here. 4, 10. So you swap the 2 in the 10. 7, 9, 18, and 12. The pivot is still going to be 5. This is my L index. This is my R index. And right now, I was pointing to this element. This was where I was. And J is still pointing to that same index element. After we complete that swap, now we can move the i's and the j's because we know for sure now element at index I must be less than the pivot. So I can move, and j can also move. So at this point now, in this situation, I can move because element in index I is 4, so I can move by 1, but j can't move. But doesn't matter. We swap, so I and the j's have crossed, which means now we partition the list into two pieces. So we'll use loop invariance to kind of prove this, but the idea is that by loop invariant, which I'll do more formally later, everything to the right of j is larger. Everything to the left of I is less than. So that means the element at index j is going to always be less than the pivot after we swap after the i's and the j's cross, which means we can very comfortably swap the pivot with index j, and it's not going to mess up this partition because the element at j must be less than a pivot because everything to the left of I is smaller. So this element at index j must be a smaller value. So now we can swap these two values, swap these two elements essentially. Because once we have the i's and j's cross, now we successfully partition the list into two pieces. So you have 4, 1, 3, 2. Now box in 5, 10, 7, 9, 18, and 12. So because we have partition work in this kind of fashion where everything to the left of I is smaller, everything to the right of j is larger, once we swap the pivot with index j, we know that the pivot element, which was 5, has to be in its correct position. So 5 will never move from this spot because we know everything to the left of 5 must be smaller, everything right of 5 must be larger, so 5 is in its correct position. But of course, we have to quicksort these two lists. So maybe I can kind of paraphrase this. Maybe I'll work these out. So we have to sort these two lists. We have to first call quicksort on this list, and then call quicksort on this list separately, and we'll have one sorted list. So let's go ahead and just do this as well. So in this case, I'm going to just now pick my pivot to be something different. So I'm going to choose maybe 2 as my pivot in this situation, just because. So I'm going to pick 2 as my pivot. So I'm going to swap the 2 and the 4. So I'm going to go ahead and put 2 over here, 1, 3, and 4. And also I'll just keep this 5 there. I'm not going to write the rest of this right-hand side of the list right now. So this my pivot will be 2. So I want to make sure I always put the pivot to the leftmost position, just so it's kind of out of the way. Just so it's not going to interfere with this partition. So whichever pivot I choose, that's fine, but just swap it to the front just to make it so it's kind of out of the way. So to partition this, well, we have to run this I and j. So once again, I is less than the pivot, increments by 1. J is larger than the pivot, increments by 1. In this situation here, well, I can move, but j can. And we crossed. So now, once we crossed, that means we partition the list into two pieces. So we can go ahead and swap these two values. So the result will be, we'll have 1 over here, 2 in its correct position, 3, 4, and 5. So we have these two lists. We have to first sort this list, then sort this list, and then we're done. Now I'm going to maybe not do any more work here, but you can see already that this list is size 1. So to sort this would be very easy. And this list, we still have to sort this, but of course 3 and 4 will be very simple to sort. So I'm going to leave this kind of open for right now. I'll do the right side as larger size, and then I'll maybe not finish it all the way up, but this is sort of the pattern. So hopefully this kind of recaps a little bit from 302. So right here, for this right side, we have to, so let's assume we have left side all the way sorted, which it already kind of is, but we have to actually run quicksort on this list of size 1, and then this of size 2, which contains 3 and 4 first, before we can have the entire this entire left side sorted. But we can already kind of do this. We can do these last few parts very simply, so it would just be a few extra steps, but I could also do those maybe later on. But anyway, for right now, let's work on the right side, which is going to be more elements here. So I'm going to pick my pivot to be 10, because I think 10 ends up being a nice pivot value. So L will be this leftmost, and then R is this. So remember, we had to pass in a new list in the partition, and we passed in a different L and R indices. So that way we know what part of the list we're trying to currently partition. So now we're going to set our I to be right after the pivot, and then J is going to go right at index R, and let's go ahead and run this again. So I can move because I is less than the pivot. So I moves, and then J can also move because J is bigger than the pivot. In this situation again, well, I can move once again because I is less than the pivot. So I moves, and also J can move. So we have this case where they crossed once again, I and J. So then now we have this list partitioned successfully. So again, all we have to do, so we have to just swap this pivot value with whatever is in index J. Because using this method, we know that since everything to the left of I is smaller, element J has to be a smaller value than the pivot. So we can safely swap the pivot with the index J value, and it would successfully break the list into two pieces. So what happened now is, I'll just put this here below. So we're going to have 9 over here, 7, and then 10 will be in its correct position. Because we know that we broke it in two pieces, then we have 18 and 12. We know that since they crossed, everything to the right of J is larger, and left of I is smaller, so the pivot being in its position is in its correct final position. So now we're left with these, these parts. So sorting these is easy. So this one, we can sort this one pretty fast because size 1 list already sorted. And size 2 list, I'll just do one of these just to kind of make it so you can kind of see what's going on here. So here, L would be R, sorry, L would be right there, and R would be right there. We're partitioning this list of size 2. And then the pivot, I'll just choose it to be L in this case. And then in this case, I would be here, and then J would be here. And then what happens is, well, J in this situation is larger, so J can move, I can't move. So J would move, and J and I do cross. So we have to essentially swap the pivot with index J, so we swap the 3 with that 3, which is going to imply that 3 is in its correct position now. So we have a size 1 list of 4, which is going to be an easy to sort list because size 1 list sorts in constant time and so forth. So these are kind of these last really silly cases here, which I'm not going to go over, but I guess it shouldn't really cause too much issue. Hopefully this sort of recaps Quicksort from CS302. So any other questions on this example that I sort of almost traced out completely? So now we want to basically prove that Quicksort does work. So this one is interesting sort of proof. It uses a little bit of induction, And induction with proving sort of the correctness of an algorithm, to me, it always seems like magic. It really is almost like magic. And recursion itself is always magic. It's nothing about recursion makes sense. It's all magic. So when you first did recursion in 202 or 302, it was definitely magic, basically. So let's go over the correctness of Quicksort. So the correctness really means we're going to prove that Quicksort does work. Now, I'm not going to have you, write out the proof for this, but it still wouldn't hurt to know this because I could have some questions on the exam, which will be maybe some true or false or something that kind of asks you some parts of the correctness. So you have to kind of know this somewhat. So you first have to prove that partition works. And we're going to do it using a loop invariant. Now, I'm not a really big expert on loop invariants, but I know enough to be able to explain this. So loop invariant is sort of a way to prove that your code is going to actually work. Loop invariant for partition has the following property. So basically, for loop invariant, so let me just put this here. So elements from A of L to A I minus 1 are less than a pivot. And then elements from A, so from A to R, maybe A of J plus 1, sorry, J plus 1 up to A of R are larger than the pivot. Yes. So if we can maintain this at every single step, every iteration, so loop invariant means that this has to be correct at the beginning, the very first part of the loop, the very first statement, and the end of the loop, this has to always be correct. So the idea for loop invariant is we have this list, and the pivot will be right over here. That'll be our pivot. And what happens is the I and the J is going to be moving. So essentially, i's and j's are moving, and I and j only moves only if the element at index I is less and element index j is larger, only then can it move. So as i's and j's are incrementing, this blue and red sort of sub arrays are getting larger and larger. So we know this is always going to hold because I and j can't move unless the element is smaller in I case, smaller than the pivot, and element at index j is larger than the pivot. So only then can they actually move. So this loop invariant is obviously going to hold. So at some point, eventually, what will happen eventually at some point is we're going to have this list over here. There's our pivot. And at some point, I will be over here, and j will be over here. So essentially, everything to the right will be larger. Everything to the left will be smaller, like this. So at some point, we have that scenario. So based on that, element index j has to be smaller, because j appears on the left of I. So that being the case, if this element goes before the pivot, it's still going to be correctly partitioned. So afterwards, you swap the pivot with the element j, and the pivot will be in its correct position because this element at index j is less. So we don't really care what the order is of the elements left of pivot, as long as they're smaller than the pivot, that's all we care about. So if we swap the pivot value with the element j value, we have it successfully partitioned. So basically, this kind of is a weird way of showing that what's it called? Partition works correctly. So the loop invariant will always hold. Even in this situation, it still holds loop invariance, so we know that it's going to partition it correctly. So the idea is just that because of this, because of these two statements, is really the reason why it will work correctly. Because these are always going to hold, because the way we have our code set up, this can never, not hold, because we're never going to move the I and the j unless we are able to legally move the i's and the j's. This was always going to hold. Now, of course, we could have it be, less than or equal, and that one will be strictly greater, or we can have it strictly less than and greater than equal. It doesn't really matter how we do it. So that's the idea. So we kind of sort of showed by vigorous hand waving that partition is going to correctly work. So partition works using this sort of loop invariant. Now we have to show, well, what about quicksort? So we have to show the proof that quicksort works for any pivot chosen. So this is actually very bizarre proof, kind of almost magic in my opinion. So basically, a size 1 list is sorted. So we start from size 1 list. So if it's a size 1 list, we know it has to be sorted array. That's kind of like our base case for this. So we're going to use like an inductive type of proof, although I'm not too strong on induction proofs. I'm really better at proof by contradiction. So even for my PhD thesis, I use a lot of those kind of proofs because those are a lot more simpler for me to kind of work at. Induction is always kind of just, I just don't like them. But anyway, we're going to use a little bit of that here for quicksort. So, all right, we have these size 1 lists are sorted. And then we have our sort of our hypothesis for induction. So we have a hypothesis that so if we're given a size n array, so so a list of size k less than n, quicksort will correctly sort this list. It almost seems like cheating in a way, but it's essentially we just assume that if a list is small enough, quicksort will just work. So all we have to do is just, okay, so using this, we have to show that, well, can we sort a list of size n? Given the fact that size 1 will work, and we just assume that for size k, it's going to also work. And k is less than n. N is the original list size. So we have the inductive hypothesis that for size k, it's going to correctly work. So when we do quicksort on a list, so when we run this list, we're going to run partition. So no matter where we're going to actually, what our pivot is chosen to be, we're going to have our pivot be in its correct position at the very end. So the pivot could be somewhere in the middle or it could be at the very beginning. It doesn't matter. The idea is we're going to create these two lists. So this will be a K1 list and K2, both of which will have to be obviously less than n. They have to be because, well, we have the pivot is not going to be in K1 or in K2. So K1 could be 0, and K2 at worst would have to be n minus 1, or vice versa. Or K1 could be a fraction of n, so would K2. So K1 and K2 are both going to be less than n. So, I'll just put this here. They're both going to be less than n. So now if we go ahead and perform a quicksort on these two pieces, K1 and K2, well, we know that since K1 is less than n, our hypothesis says that it will work. on size list less than n. So which means that the left side will be sorted, the right side will get sorted, and therefore we have the pivot, which is going to be in the middle of these two sorted lists. Therefore, quicksort works. Yeah, so that's really a wacky proof, but that's how induction works. So we have this base case, inductive hypothesis. So we just show that it works for these two size lists. If it works for these two size lists, then it has to work for the entire n, because these elements are all less than the pivot, all larger than the pivot on this side. So that means this whole list will be one sorted list, because we're going to sort this K1 list and a K2 list, and everything in K2 is larger than everything in K1 and the pivot, so that means you don't have to do any additional work anymore once we sort K2. And same thing for K1. Everything K1 is less than K2 and the pivot, so we sort K1, then we have a sorted list, then P, another sorted list, and we know that everything in K1 is less than the pivot and less than K2, and everything in K2 is larger than the pivot and larger than K1, therefore it has to work. So that's sort of the proof that quicksort does work. So we're going to go ahead and do some further analysis on different types of pivots that can be chosen and get the runtimes based on that, because really quicksort depends really on the pivot chosen. So we'll do some analysis of runtime of quicksort and pivots chosen, and also talk about ways of how we can actually guarantee quicksort is going to work nicely. In other words, how do we find a way to make sure that we are guaranteed to pick a good pivot to ensure that quicksort has a good runtime? So we'll work on that next week. So I guess for right now, that'll be it for today. So I guess take care, you guys. Stay safe. Have an awesome weekend. Thanks for watching, and I'll see you guys on Tuesday.